Welcome. Welcome all to the Sustainable Development Goals session. My name is Kelly Wanzer. I'm the Executive Director of SilverLining. You are in the session on the transformational possibilities of equity and climate science research for the Global South. I'm really pleased and honored to be invited to moderate this panel. It's a really wonderful and interesting panel led with climate experts who run climate research labs in the Global South. And we're going to be talking about an issue that may not be high on people's radar. I think part of the issue that's high on people's radar is how important climate research and climate data is to the topics that arise in terms of impacts, in terms of loss and damage, and in terms of decisions about climate change. What's been maybe less high in awareness is how that's linked to the resources, both financial and technological, available to experts in the Global South who have the talent, but they don't have the capacity. And part of that capacity has to do with technology. And that issue is being brought forward by some of the people that are joining us here today. So I'm very honored to introduce our first speaker, who's going to be joining us from Cape Town, South Africa. Chris Leonard is a senior climate researcher at the University of Cape Town in the Climate Systems Risk Analysis Lab. He leads a team there of researchers who do advanced climate modeling and impact studies, and they've looked at questions like hydrology and drought in South Africa and Southern Africa. And they've looked at some questions around climate interventions, which is an emerging area of research. And they're sort of pushing the edge of what's in the art of the possible. And so Chris is here to talk to us about the work that he does and how it's tied to some of the issues of capacity and technical challenges. Welcome, Chris. Thank you very much for being here.
Hi, Katie. Hi, everyone. Thanks for the invitation. It is really nice to be here and to chat with you. Let me share my screen quickly and we can get going. I've been asked to largely just chat about climate models and climate modeling in general and how and why in the Global South we generally can't do this. So hopefully I'm sharing the screen nicely and you can see it. So let's jump right in. I've titled this Climate Modeling for Climate Science Equity in the Global South because climate modeling is really important. Let's just start at the beginning with global climate models. So global climate models is how we get to where we are going to in the future. We basically give the climate model a series of scenarios, and the climate model will then tell us, okay, by 2100, we'll be at 3 degrees above the prehistorical. We'll be at 4 or 5 or 6 or 2, hopefully, maybe even 1.5. But the question is, how does the model do this? And that's what I'm going to try and get into. So you have in front of you a schematic of a global climate model. They call it global climate models or general circulation models, depending which community you're speaking to. And what these models try and do is simulate the ocean, the atmosphere, the biosphere, so all the land surface processes on the globe to give the best representation of the Earth system. In CMIP 6, the latest generation of climate models are called Earth systems models. And the Earth systems models try to simulate all the components of the Earth system, including the physical components like the atmosphere and the ocean, and then also the biosphere, so the more dynamic components of the biosphere too. And the models do this largely through dividing the atmosphere and the ocean up into cubes and then computing thermodynamics and mass balance equations. So how does energy move from one cube into the other? And then what does that mean for rainfall? And what does that mean for wind and temperature and a host of other variables? And in doing that, the climate model produces the best simulation of the Earth system that it can. There are a number of climate models, global models at the moment. I think we're up at about 70. And each of these models is doing essentially this. So you have 70 representations of the Earth produced by these models. And this is how we can go into the future, because we can tell these models, okay, there's going to be greenhouse gases input into the atmosphere. What does that do to the system? So these global climate models are the way we see the future. In climate modeling, scale is really important. So what you can see there is just a map of scale. And at the global scale, we really talk about processes that last months to millennia. So here we are thinking about the seasonal cycle, or maybe the El Nino Southern Oscillation, so ENSO. But then importantly in that graph that you can see with the curve going up is also how are greenhouse gas concentrations increasing as we go into the future, because as you know, it has a global effect. So the climate model has to see these large scale months to millennia types of processes. But then it also needs to simulate hemispheric, so not quite global, but processes that last from days to weeks and perhaps edging into months too. And here we're thinking about processes like cold fronts, tropical cyclones, atmospheric rivers, and a host of other synoptic scale processes that we know of. And the last scale that we need information for about the climate is at the local scale and the regional scale. And here we're talking about processes that last seconds to hours. And this might be thunderstorms, a really cool supercell picture that you can see there, or tornadoes, or dust devils, or turbulence. And this is an important scale because this is the scale that we live at, really, and where we get affected. And global models, as you'll see in a moment, are not really designed to produce information at this scale. So then for our atmospheric model, the global models are well suited to doing those larger scale types of processes that condition the global scale dynamics, but they're not that good at getting all the way down to the regional or local scale, so if you simulate local dynamics. And this is important to know because impacts occur at our regional and local scale. So a flood is not going to happen on a global scale, it's going to happen at a regional or local scale, or a drought. So we need to get to producing climate information at this regional and local scale. Why is this scale important? It's because impact is a function of risk, and risk is a function of several things. The first is hazard. So where you see, this is called a risk propeller, and we introduced this figure in our IPCC Africa chapter in working group 2. And risk is a function of climate hazard. So that H stands for what is the climate hazard, the exposure of the population or region to that hazard, then the vulnerability of that population to the hazard, and which is also a function of the exposure, and how can you respond to a particular thing. And these 4 factors contribute to the risk that you might face from a particular climate event or climate change. Where is local climate information critical? So where is risk highest? And this is a map of vulnerability, and where it's purple, where the shades are purple, it's showing you regions of high climate vulnerability. And you can see Africa, where there's a dark purple, is the most vulnerable continent to climate variability and climate change. So there's this band of vulnerability in the tropics and the subtropics, and also particularly in Africa. So we need to understand the climate change impact in these regions at a regional scale where people live. So how do we try and address this question of scale? This map represents what you might see in a global climate model, where each grid cell that you can see there will give you one number for temperature, one number for rainfall, and for wind. And if you look at Cape Town in the bottom southwest corner there, you can see the grid cell representing Cape Town is largely in the ocean. But Cape Town is a lot more complex than that. We have topography that goes up to 1,500 meters or more. We have very flat areas. We have the ocean. So it's a very complex region to try and simulate. And if you use just that climate model data, you'd not get the type of information that you need. So what we do to try and get from that global scale to the more local and regional scale is through a process called downscaling. And I'm going to be talking about what we call dynamical downscaling, where we use what are called regional climate models. So GCM there stands for Global Climate Model. And what we do is we nest a regional climate model in a global climate model just over our region of interest. So this example here shows Europe, where there's a regional climate model nested in a global climate model. And the global climate model could give you information every 200 by 200 kilometers. You'd get a value for temperature, for example. But the regional climate model, you can now say, okay, please give me a data point every 5 kilometers or every 10 kilometers or 20 kilometers. So you're moving from a very coarse scale to a much finer scale. And that finer scale data is often what impact modelers in the impacts community are interested in. So people who do hydrology modeling or agriculture modeling or energy modeling need this information at a much higher resolution scale. So the scale is going to be at that local and regional scale that we spoke about earlier. We know that downscaling does add value to what the GCMs produce. They give a lot more insight in regions of topography and along coastlines. They give physically consistent results so we can understand why we see what we see coming out of the climate model, the regional model. The data is often more useful for impact modeling, as I just said. And also when you do very high resolution modeling, up to 2 kilometers or 1 kilometer, we've seen time and time again that it improves rainfall, the representation of rainfall, the simulation of rainfall, and other variables in the models. So downscaling definitely does add value, but it is computationally an extremely expensive exercise, because every time you halve your resolution, so if you go from 10 to 5 kilometers or 100 to 50 kilometers, you increase your computational requirement by 4 times. And if you live in a developed nation where you've got in the US, here in Boulder, they've got Cheyenne, or in the UK or in Europe, there are these massive supercomputing infrastructure that is there. But in our most vulnerable regions, we just do not have this type of computational infrastructure. So how do we get this regional information that we need, or this regional climate data that we need? Because it's a huge barrier to producing adaptation information in Africa. So we're vulnerable, we know what's coming, we need to adapt to it, but how do we get to that information? How do we know that we need to adapt? Keeping in mind that the modeling tells us where we go to in the future. And I'm just going to touch on 2 things here. The first is on finance, so climate research finance on Africa. We're reporting this in our Africa chapter again, so I've got the IPCC logo at the top there. And between 1990 and 2020, only 3.8% of global climate change research funding was spent on Africa. So on that curve at the bottom, you can see the blue represents global expenditure on climate change research. And the orange curve that hardly leaves the 0 line is the money that was spent on Africa. If you thought it couldn't get worse, it does. Where does that money go to? It largely goes back into the developed nations. So to the US, to the UK, and to the EU mostly. So what this is telling you is that climate research being done on Africa is largely being done by developed nations in the US, the UK, and the EU, by developed nation scientists. So what I don't show in here, but what we see is that when you punch the numbers, you actually figure out that only 0.8% of the funding for global climate change research between 1990 and 2020 actually went into Africa, so went to African scientists. And this is not great, because for a number of reasons, but the reasons I'll go into is largely because it reduces the adaptive capacity in Africa to prepare for the future, really. Because if you've got northern scientists doing science for Africa or for South America or for Asia, it brings the global north perspectives of adaptation into that region. So you're trying to, the global north is trying to force the way that they would do things onto the global south, and that can't happen. Because the regional context is not considered, you're not considering the ethical values of the region that you're interested in. So it really is a mismatch. And there's usually no co-production of relevant or actionable information being developed. Then also most African countries have very low levels of adaptation research. So this is a map showing the number of scientific papers that have been written on adaptation in each of these countries. And again, you can see Africa, where it's these light pinks, there's hardly any papers have been written. There's 1 or 2 spots. But you can again see that the situation is not good. What's even worse here is that of 15,000 papers that were reviewed or looked at, 60% of those papers did not include an African author. So here I'm again just focusing on Africa. So adaptation research is being done by northern scientists, and they're not bringing in southern scientists. So again, the whole context is not there, it's lost. But let me bring it back to modeling now. So how do we enhance climate modeling capacity in southern nations? And as an African, this is where I live. because the climate modeling sets the basis for how we go about adapting to climate change or thinking about adaptation and mitigation of climate change. I'll just mention one example that involves SilverLining's CSAG, where I work at the University of Cape Town, and Amazon Web Server, where we're moving into the cloud. So we don't need this massive infrastructure, those big computational centers that I showed you earlier that are at NCAR and in the UK and in the EU. But we do all of this modeling on the cloud, and we can, if we run our climate models in the cloud and we keep our data there, we can run the analysis on the data in the cloud. And this capacitates Southern scientists who don't have access to this computational infrastructure that we saw earlier. And this is something that we just started for the coordinated CORDEX, the coordinated regional downscaling experiment, and we got our first results out. This is a test phase, but we got our first results out last week rather. So there are things that we can do to enhance climate modeling capacity and understanding where we're heading to into the future. And my view is that as Southern researchers, we can do this in the cloud. We have to do this in the cloud. We can't actually build these massive compute infrastructure that other nations have. So I hope that was useful, and over to you, Kelly. Thank you.
Thank you, Chris. That was really useful, really clear, and really powerful. I have a couple of questions, and we're going to keep you around because others are going to have questions too. But just to be clear, so your work in the climate modeling you described up to this point, what computing capacity do you have access to at the University of Cape Town?
Yeah.
And how much of a constraint is that now? Yeah. And that's in the context of the University of Cape Town having maybe more resources than most places in Africa.
Yeah, so we have a relatively good, in the context of Africa, as you said, relatively good computational infrastructure. We have a small cluster, or we consider it a large cluster, but anyone from Europe or the US would consider it very small. It's like a basement type thing. So I've just run an experiment. So for that, those graphs, those maps that I showed in the last slide for CORDEX, we managed to run that at CSAG on 80 nodes. So we have 80 nodes available that we can do those simulations on. I then ran those simulations on the Amazon Web Server, where we used 480 nodes, and it sped up the computational time by 15 times. So it ran 15 times faster on AWS than it did at CSAG. And if you think that AWS is kind of similar to what is available at these big computational infrastructure like UCAR here in the US or the Med Office or in the EU, then that's where we sit. So in CSAG, we've got a decent compute resource, but it's really small if you think about it.
And this project that you described to do downscaling, how much relative computing does that take? And it sounds like the project would have value for lots of researchers who want to look at that part of Africa. And what do you think that would mean in terms of the climate science capacity or capability if you're able to do it?
Yeah, it's huge because the data from CORDEX, the Coordinated Regional Downscaling Experiment, gets used a lot by African researchers. And again, I'll speak for Africa because it's my context. And different communities, including hydrology, agriculture, health, all use CORDEX data. And this CORDEX data now is probably 7 or 8 years old that is being used, and it's at a resolution of about 50 kilometers. So it's not super high. What we're wanting to do in this cloud computing exercise is run CORDEX experiments to downscale CMIP6 climate models over Africa. And again, this can then get used by the various communities. The trick here is that whereas in the previous version of CORDEX, what we would have to do is get data onto disks. So in Cape Town, we would buy a whole set of external hard drives, put the data on the portable hard drives, and then basically ship them to our scientists all around Africa. But with this AWS idea is to do the simulations in the cloud, but then also leave that data in the cloud and have our scientists do the analysis in the cloud. So we don't have to shift disks around, and we don't have to worry about disks breaking down and then people losing all of their work. So the idea of cloud computing, I think, is massive, and it's revolutionary for us as Southern scientists because it gives us access to data that we didn't have access to before. And that then starts the chain where we can then move on to thinking about how does this affect adaptation? What does this mean for mitigation? And it builds capacity in Southern researchers also to work with this data because we just don't have it. So we can't work with it. And we'll never, if that stays the same, we will never be able to achieve the same types of research that European and US and developed nation scientists reach.
Thank you, Chris. That is a powerful explanation, and it's also a really great introduction to our next speaker. So please stay here. We're going to hear from our next speaker who has done some recent thesis work on these topics, looking at Africa and the question that Chris was speaking to, which is the question of, what does it mean for scientists and experts around Africa to be able to have capabilities and capacity that they don't have currently. So Maddy Carlsberg-Schaefer is currently leading the Global Youth Initiative at my organization, SilverLining. So Maddy is recently completed an MSc, a Master of Science in Governance of Sustainability at Leiden University in The Hague, Netherlands, where they have an interdisciplinary science policy program. Previously, she was a researcher for the Scottish Communities Climate Action Network and a member of the grassroots pressure group Fossil Free Glasgow on a campaign that resulted in the University of Glasgow becoming the first academic institution in Europe to divest from fossil fuels. So I'm quite moved by that, Maddy. She holds a first-class honors degree in geography from the University of Glasgow. She's been in the Netherlands, and she's also recently been in South Africa and Malawi. So please tell us about your work, Maddy. Thank you.
Thanks so much, Kelly. Yeah, so thanks everyone for being here. I'm really excited to share this research with you, which was actually kindly funded by SilverLining. Yes, so you know a bit about me now. And yeah, for the second year of my master's thesis, the second year, I had to complete a master's thesis, and I chose an investigation into the barriers and opportunities to climate modeling in Malawi and South Africa, because this equity issue really, really interests me. So yeah, the basis for this research, well, I think we've got some good context already from Chris, but I'll go over the basics. So climate information is obviously an essential tool for climate resilient development, be it adaptation, disaster risk reduction, etc. And climate modeling, as Chris showed us, it's integral to producing that climate information. And when we look at climate vulnerability, that is most acute in the global south, but particularly in Africa. But most of that climate modeled information on the African climate is undertaken by non-African scientists in the global north. So that led me to ask, what are the barriers and opportunities to producing this key research in the African context? What issues are at play and how can we overcome them? And today I'm going to focus more on the barriers and particularly infrastructural barriers. So why South Africa? Well, it arguably has the highest climate modeling capabilities in Africa. That's infrastructural, human resource, institutional, etc. But by choosing the best capacitated country, this actually gives a good degree of showing what is the extent of African excellence in climate modeling science. But at the same time, by doing that, it doesn't give a good indication of what is the situation in the rest of Africa. So what I did a comparative case study, and I chose Malawi as my second country. So current research indicates its capacities are more in line with neighboring African countries. And its National Weather Service is the only institution, or at least research indicated it's the only institution active in climate modeling in the country. And another nice reason why I chose it, well, I'm a Scot, and there is something called the Scotland-Malawi Partnership, which is a Malawian-owned and Malawian-led network established to support and develop Malawi's civil society links with Scotland, which date back to the 1850s. So it felt like a natural selection to go for Malawi. So how did I investigate these barriers and opportunities? I did it through interviews, and I did it in country in South Africa and Malawi with 21 separate interviews. There was a lot of data to sift through, and that was with individuals from government departments, so policymakers at environmental affairs departments, but also science, tech, and innovation policymakers too. Modelers also at either National Weather Service and also at universities and research institutes. My first theme of results, that regarded computing power limitations, which Chris has kindly given a solid basis for already. So we do need supercomputers, powerful computers to run climate models, particularly those downscaled models which run at a higher resolution. You can see in the graph in the bottom left corner here, how downscaling improves the resolution, increases the resolution of a climate model, and thus the detail. And so as that detail is increased, the more computing power is necessary. So my research in Malawi basically confirms that its National Weather Service is the only active institution in climate modeling science. So there's no universities or research institutes involved. But even at the National Weather Service, their supercomputer facilities are nowhere near even the capacity seen in South Africa. So, for example, one of the scientists, he told me that it was taking 6 months to run a regional climate model, a downscaled model, in order to get an output for one singular month. So if you're trying to do any long-term climate planning into the future, it's almost pointless. So it led them to actually giving up. In South Africa, as we know, it's better off. It's home to Africa's most advanced supercomputer, actually. It's what Chris works on. But even then, actually, Chris was one of my interviewees. And Chris, if you remember, you told me that it would take you over a year to run a certain experiment when it would take one of your Danish research partners 3.5 months. So that is kind of the level we're seeing from Malawi to South Africa to Global North Institution. And ultimately, the cost of these supercomputers is a huge obstacle. So just to give a kind of idea, Orion, the new supercomputer at Mississippi State University, that cost $22 million to initially procure, install, and run. That kind of money is not what countries like Malawi and also South Africa are looking at. And what are the impacts on decision making? Well, the inability to conduct experiments forces decision makers basically to rely on less accurate sources of information. So that's, the modeled outputs of global climate models, which we saw in Chris's presentation, which are at too low of a resolution to really be useful for decision makers. So that seriously impacts local decision making, local and national and regional even. So the second theme of results regarding infrastructural barriers is climate observational data and data availability and access issues. So climate modeling requires the input of continuous, consistent, and long-term observational climate data. So that's like temperature and precipitation in order to generate accurate and reliable results. And so in Malawi, figures over there, they emphasize that vast swathes of the country remain unobserved, and the data sets that they have are either inconsistent or there's missing data. And also, a lot of these data sets are too new to be useful for climate modeling. They only start a few decades backwards, so we can't really use them reliably. Meanwhile, in South Africa, well, they have a higher density of stations, but key issue faced there is data ownership patterns by different organizations that manage the stations. And often the data isn't free due to funding constraints. And that's actually the same in Malawi. So implications for decision making. Well, the climate projections are basically less reliable, especially in Malawi. But something that particularly struck me, I'm not sure if you can't really see the bullet point on the screen, so I'll just say it out loud. What really struck me about this data access and availability issue is how can we possibly operationalize a loss and damage system if we don't have the data there to do climate attribution studies. So, for example, if there's an extreme climate event and we need to be able to study it as it unfolds and be able to say, okay, this was a result of climate change rather than natural climate variability. How can we do a study like that if the data isn't there, or if an organization that owns that data refuses to share that data, or it's too expensive for people to work with? And that's actually a problem seen in South Africa, or at least the interviewees that I was in contact with mentioned. I arrived in South Africa right after some really devastating floods, and they mentioned, you know, like, we can't do attribution studies on time. It's not possible. So that was a big jump out take home message for me. And the third theme is on power and network supply. So power supply is required to run a model on a supercomputer, but also sufficient internet bandwidth is also necessary for exchanging and downloading input data. In Malawi, ironically, the electricity grid is running well below capacity due to climate disasters. So there's a lack of power there. Power surges actually damage equipment, and this equipment is really expensive and really hard to bring into the country and fix with the developers or manufacturers rather that are mostly situated in the global north. Also, the slow bandwidth in Malawi means that data sets take up to 1 week to download, also a hindrance to research. In South Africa, there's government-controlled electricity rationing and power outages, so this can interrupt model runs, reinitiate the installation of like the libraries for in the software, and this can also cause the corruption of code. So altogether, this basically slows down the pace of research. But there are also actually knock-on effects to these infrastructural obstacles. So, for example, in human resources, this impedes skills building, training personnel, and teaching students. And also actually institutional research capacities. You know, you can't build up a research culture, research reputation if you don't have the facilities and the qualified personnel to do that research. And overall, I found that these impacts were indeed worse as expected in Malawi than in South Africa. So to conclude, how do barriers to climate modeling impact research in Malawi and South Africa? One, the scope of possible research is limited by infrastructural issues. Number two, the foundations for evidence-based climate policy is relatively unreliable, inaccurate, or unavailable compared to the global north. And three, infrastructural barriers in turn reduce human resource and institutional capacities. Thank you for listening.
Thank you, Maddy. I'm going to have to pass this back to you because I have questions. That was really powerful and amazing work. Really amazing. I know you work with me at SilverLining, and we look at near-term climate risk and how people might make decisions about what to do. And we get to interact with researchers in the global north who have access to Mississippi State and other things. But what I hear you saying is, in a place like Malawi, you have these escalating impacts, which are causing power shortages. They also don't have the computing to do the types of modeling and data studies that Chris described, but they're being asked for the evidence to produce that you need to do loss and damage problems. And that capacity is getting worse, not better. Is that right? So how did you start to think about that in terms of some of your master's work on, issues of climate equity and justice? Like, How do you think about that?
Kind of the first thing that came to mind was, oh dear. it made me realize the scale of the issue we're facing. Because when it comes to things like power, electricity supply, these really key things that are necessary for supercomputers, for example, these are broad infrastructural issues that span well beyond climate science and climate research. So it needs a really integrated, well-rounded, holistic response. And I don't know, I felt that we have a mammoth task at hand, and also with like observational networks, they're actually falling out of use, both in South Africa and Malawi. So we've got underinvestment, climate impacts worsening, and yet it's kind of a bleak picture. I'm not going to lie.
Well, I heard some hopeful things in what Chris was saying about what might be possible to do. And so I think we'll talk more about that. But before we do, the picture that you're describing and Chris is describing is not unique to Southern Africa. It is a common picture across regions of the world that Chris showed in his slides. And so I'm also really honored this evening to have a very senior scientist who's been contributing in climate research and on climate impacts for a long time, facing this limitation and trying to figure out, how to work within it. So it is my pleasure to introduce Dr. Abu Syed from Bangladesh. So he is broadcasting live from Bangladesh, and he is currently the Environment and Social Safeguard Specialist of the World Bank, supported by the Livestock and Dairy Development Project. He's a senior fellow of the Bangladesh Center for Advanced Studies and founding director of the Nansen Bangladesh International Center for Coastal, Ocean, and Climate Studies. He has 28 years of experience working on multi-country programs on climate modeling, climate risks, and vulnerability, including assessment, mapping, adaptation and resilience studies, investment planning. He's currently the principal investigator of an ongoing research effort on solar climate interventions, which are possible rapid interventions in the climate system. And his work has spanned work for Bangladesh, for Qatar, for Western Africa, for parts of Asia. And he also is currently one of the key experts of the National Adaptation Plan and Capacity Building for Bangladesh. He leads a group of researchers operating from Bangladesh, looking at climate impacts and response questions. Dr. Syed, thank you for joining us. It's a pleasure to have you here.
Thank you, Kelly. Good evening to all the audience.
You gave the example of climate intervention, of the sort of big idea to put aerosols in the atmosphere to try to cool climate, and how you're very interested from the perspective of your organization in Bangladesh to try to study the questions associated with the risks of that and what it might mean directly from your research team there. And that the limitations that Chris Leonard described are limitations that prevent your teams in Bangladesh and people in Bangladesh from doing what you think is needed to look at ethics, decision-making for this kind of problem. Is that right?
Yeah. So the issue, as I said, from my research experience, with at least for climate intervention and climate modeling, what I have been doing, one major issue is that we don't find young scientists to do these works there in Bangladesh. Mostly whoever gets some training in northern institution, they live there or they come and go back to the institutions in the northern institution. One thing. The other thing is that the computing facilities. So we don't have that institutions in Bangladesh who can run all these supercomputing facilities or establishing these facilities. I know what I did also another institution like some universities and institution. They're also using cloud computing with other institutions in collaboration with UK or some universities, and I have done myself with Bergen University computing facilities. I used that, but we don't have that facilities in Bangladesh, whether it is infrastructure or superstructure or soft skills.
And the kinds of study that Chris Leonard described with the downscaling to look at impacts.
Yes.
Are you able to do that for Bangladesh?
Yes, downscaling we could do with only one particular model we have done with WRF, that is Anchor is mostly running the weather research forecast model we have done, and we have found some potential impacts which has been reported and published earlier. So to do this one, particularly this one, I think we don't have the downscaling facilities at this moment.
Well, thank you. Thank you very much. So we're actually closing out here in Sharm el-Sheikh. So we need to say goodbye to you, Dr. Syed, and also Dr. Leonard from South Africa. And really thank Maddy Carlsberg-Sheikh for starting a dialogue around these issues. We heard that there are a couple of very important topics for Global South climate researchers and Global South stakeholders, which are loss and damage and understanding impacts and the possibilities of these sort of different responses, including, you know, the end of the spectrum of climate interventions. And that among the many challenges, one of the challenges is actually infrastructure and computing. And that there might be some ideas that Chris hinted at that might get us quick help in getting better Global South access and resources for that. So Chris, thank you very much for joining us. Dr. Syed, thank you for joining us. We hope that you'll be hearing that you're advancing on these projects and that you're doing more work and you'll be coming back to us with the science. So thank you all for listening and joining us. Thank you, Maddy, for your work. And we'll sign off now from Sharm el-Sheikh.
Thank you all.